All right, welcome everyone to today's Astroparticle seminar. And today I'm very happy to have Shirley Li as our speaker. Shirley did her PhD at the Center for Cosmology and Astroparticle Physics, CCAP, at Ohio State University, where we met. Then she was a postdoc at SLAC, National Accelerator Laboratory. And now she is a postdoc at the Fermilab Theoretical Physics Department. And Shirley has worked on a rich mix of theoretical, phenomenological, and experimental work. Includes detailed cosmic ray muon spallation backgrounds in MEV neutrino detectors like the Super K and Dune, and ways to mitigate that background. She's worked on high energy neutrinos and for instance, new ways to distinguish between flavors in IceCube. Supernova neutrino detection in Dune, of which she is a collaboration member, and other liquid argon neutrino detectors. She's also worked on lepton-nucleon cross-section measurements and leptonic unitarity triangles. And today, we're lucky to have her talk about one of her latest works on late-time neutrino emission from core collapse supernovae. And as usual, you're welcome to ask questions during the talk. Just raise your hand, and you can just ask it yourself. You can also just write it in the chat box, and I can read it to Shirley when I find the right moment. All right, Shirley, take it away.
Thank you very much for the nice introduction, and thanks again for the invitation. Because I'm just paranoid about having internet problems, I'll turn my camera off while I give the talk. So, okay. So when a massive star dies, it undergoes core collapse supernova and emits copious number of MEV neutrinos. If this happens in our galaxy, we can detect thousands of neutrinos and will gain incredible information on supernova mechanism, neutrino properties, and maybe new physics. So today I'll talk about the general prospects of detecting the next galactic core collapse supernova in the current and upcoming neutrino experiments, and focusing on the late time. And because this is a subject with extremely rich physics, I'll pay particular attention to explain the scales of the problem and just general orientation. And please interrupt with any questions you might have. Okay, so whenever I talk about supernova physics, the first question after the talk is always, when will this happen? So of course I can't possibly know that, but generally the expected rate of galactic supernova is often quoted as 2 to 3 per century. So here I just want to emphasize the point of how uncertain this number is, and that it's, from a non-expert, it looks like it's very difficult to improve the precision of the prediction. So there are actually quite a few methods that people use to determine the core collapse rate. So I find these two the easiest to understand. So the left number is from the so-called historical method. So basically what happens is in history, there are 5 recorded galactic supernova after 1000 AD. So when a historical record is considered complete. So we can infer from records of how bright these supernovae were. And of course, we know in which country it was observed. So roughly where on the sky it is. So then if you have a complete model of the brightness distribution of all galactic core collapse, including their location distribution, and you can sort of infer what is your coverage or completeness. And so then, given that, you can infer a total galactic supernova rate. So from this, I would say it's not surprising that the errors are pretty large. And I want to point out that the statistical error from having detected 5 supernovae is actually a subdominant component to the total error bar. So roughly speaking, 5 events should give us 40% error, which actually is only about plus minus 2. So you see so on both directions, the errors are actually much bigger than that. And actually, it seems like in more recent years, more complete galactic modeling of the galactic supernova actually leads to larger error bars. So that's the left number. And on the right, I think it seems the method that seemed like it would be more precise. But notice that the end result actually have a systematic uncertainty of a factor of 2. So what this number comes from is that there are basically dedicated astronomy programs looking for supernova on the sky. So for this work, the program LOSS is used, which has data on about 1,000 supernovae from nearby galaxies. Then you're essentially doing the same thing because you can model all the galaxy types that host supernovae and compare to what you observe. and you know your telescope's efficiencies and coverage. So then this gives you the local supernovae rate. So these two and several other methods all give roughly consistent results. But you can see that the systematic errors involved are all pretty large. And so it seems like a number that it's hard to get more accurate. And I think there perhaps a misconception that in recent years, the predicted number went from either 3 to 2 or 2 to 3. I think at the confidence level, that sort of a change will not happen. Okay, so we'll just have to wait, and it's going to happen sooner or later. So since we talk about when, let's talk about where. So here I just show the standard expectation of how far away will be the next core collapse supernova galactic. So let's look at the top plot. It shows the probability distribution, and let's look at the black line. So the peak is, and the median is around 10 kiloparsec. So that's a little bit further than our distance to the galactic center, which is about 8 kiloparsec. And I think on the order of magnitude scale, this distribution is actually peaked pretty narrowly. So what do I mean by that? So roughly speaking, within 80% likelihood, the supernovae will be between the distance of, say, 5 kiloparsec to 15 kiloparsec. So the flux scale is as 1 over d squared, which means that if we assume the standard distance of 10 kiloparsec, which is the literature average, then the flux will be either up or down by the factor of 2 to 4. So, which is significant, but it's not like the flux will change by orders of magnitude. That's highly unlikely. I also want to point out on the bottom, which shows a cumulative plot. One message is that it's actually incredibly unlikely for the supernova to be either within 1 kiloparsec or larger or further than 25 kiloparsec. So that just sets the scale of roughly where do we expect the next supernova to happen in the galaxy. Okay, so but as we all know, we actually did detect a supernova. So supernova at 1987, where we detect about 20 or so events. And so first thing to point out is that actually happened in large magnetic clouds. So that's 25 kiloparsec away. And from previous slide, we can see that actually that's a kind of unlikely event. It's on the distance scale. But for the 20 or so events, we've actually gained incredible information on core collapse supernova. So these 20 or so events confirmed our basic picture of core collapse supernova, meaning that almost all of the gravitational binding energy are carried away in the form of MeV neutrinos. And the time scale of the explosion is about a few seconds. And that all the energies are roughly equally divided between all 6 flavors. 6 mean that nu e bar, nu mu bar, nu tau bar. And that the energy of the neutrinos are somewhere between 10 to 50 MeV, and they have a thermal-ish spectrum. So, but it's also important to point out that as incredible as these neutrinos are, because there's only 20 or so events, and because of the detection quality, they're not good for a precision measurement if we really want to understand supernova. For example, this is a paragraph taken out of this nice review article. Here they point out that data are not sufficient to discriminate between equation state or to validate specific details of the models. So, which of course is not surprising because it's 20 events after all. And I emphasize this point just to highlight the sharp distinction between what we can do with the next supernova. Okay, so with 87A and with the decades of theory improvement, theory progress, we understand a lot about supernova. But I would say there's plenty of open questions left in the field. So for example, we still have not fully confirmed that the delayed neutrino heating is the correct explosion mechanism that revived the shock and drive the explosion. And although we know a lot about how neutrinos oscillate in supernova, we still are not able to fully compute how it happens and to test it in experiments. And we know that supernova are said to produce heavy elements, but we don't know how much of each. And we sort of know the correlation between the remnant of the supernova, meaning whether we get a black hole or a neutron star, and what's the mass of the progenitor star. But we still don't know with full confidence what remnant will we get if we explode a 15 solar mass star. So, and you can probably add your favorite questions to the list. And I would say the ultimate goal in the field is that we can compute these things theoretically within different groups so that we know we can all converge on the same answer. And we want to confirm these experimentally, which of course seems insanely difficult. But I would argue that we possibly have one chance to at least get very far on that scale. And the best case scenario would be if we get a supernova in the year 2030. So let's look at what could possibly happen with a supernova into 2030. So compared to a detection of nu E bar only, we can possibly detect all 6 flavors, nu E bar, nu E, and because in supernova, roughly speaking, there's no difference between nu mu, nu bar, nu tau, nu tau bar at the leading order, so I'll call all of them nu X. So for the next one, we could possibly cover all 6 flavors. And instead of at 25 kiloparsecs, it's very likely that it's going to be more, it's going to be closer. So let's put it at 10 kiloparsec. And instead of 20 events, we would expect of order 10,000 events from all major experiments combined. And as opposed to a 10-second event, this burst in detectors will last about 1 minute. Now, comparing this, I do not want you to take away that the main difference is 20 events versus 10,000 events, which means it's going to be a factor of a square root 500 more accurate measurements. That's not at all the point. The point is that it's going to be quantitatively different measurement. The one on the left column is great for basic testing at that, we're not completely misunderstanding what's happening in the supernova, but it's not a precision measurement at all. And on the right, with basically quantitative difference at every aspect, we can have a chance to actually carry out precision measurements to measure a lot of unknowns that we actually don't know from theory in experiments. Okay, and I want to emphasize the point that if supernova happens in 2030, I would say we will be really, really lucky. But the opportunity to actually carry out such a measurement that's on the right column don't actually last forever. So to measure all 6 flavors, what we need is first a big detector measuring E bar, and that's currently ongoing Super K, which will have a Hyper K later. And to measure nu E, we have Dune, which is under construction stage. And to measure nu X, we have Juno, which is also under construction stage. But these detectors, but especially for Dune and Juno, it's actually not clear whether we'll have successors. And they're scheduled to run for quite some time, through 10, 20 years. But after that, it's not clear what we'll have. So the reason is all of these detectors are primarily going after mass hierarchy and CP violation, which is oscillation physics. And so it's hard to imagine that once we've actually measured mass hierarchy and CP violation, which are the last 2 unknowns of the whole oscillation program, that we can get funding for another big detector just to go after supernova. And in addition, as we need larger and larger detectors, I think it's fair to say that on the water and oil front, we're sort of reaching how big these detectors can get. So at some point, detectors are so big that light will get significantly absorbed inside its own tank, and that's just getting much more expensive to scale up. And I think for Hyper-K and for Juno, we're already reaching there. So for all these incredible detectors, we probably will have a window of 10, 20 years where they're all online, they're all functioning, and after that, it's not clear where what we'll have. So we really just have one time window for detection. And so it's important for us to help these detectors get as ready for supernova as we can get. So what does that entail? Well, I think as theorists, it's incredibly important to point out all the physics opportunities that we have with the supernova detection. And from an experimental perspective, if you read all the experimental white papers and etc., I think there are a few science cases that they have in mind, and that's very well studied, like the importance that they deserve. So the first one is pointing the supernova. This is using early time, sometimes using multiple detectors to pinpoint where on the sky the supernova happens. Of course, this is very important because if we can do this, then we can tell optical telescopes to point there so that we can have optical follow-up. And other quantities that experiments studied very well is how well we can measure average energy and total energy. And if you look at, again, experimental white papers, all the sensitivities on these quantities are just how you would imagine. However, there's almost no other science cases you can see from on the experimental side. Whereas there's so much more science case. For example, how well can we measure equation of state? How well can we measure a black hole formation? And name any questions you have. So somehow I think this is not specifically just tied to my study, but I think it's an important miscommunication in the field, that as theorists keep making progress on many questions and also including sensitivity studies, it seems like those kind of message have not gotten to the experimental side. So hopefully we can do better at communicating more science opportunities so that we can have better sensitivity studies. Any questions up to this point? No? Okay. Then I will talk, next I will talk about the timescale of a supernova, also defining what I mean in the title of what is late time. So this slide will take some time. So here I show the nu E bar luminosity as a function of post-mass time. So I divide up the plot into 3 main regions, and let's look at the curve and the colored patch. So first, for negative time, this is essentially before collapse have happened. So this is called the pre-supernova stage, where there's very, very little neutrino emission. And this emission are coming from basically the late stage of stellar burning, so silicon burning. So in physics sense, this is more similar to the solar neutrino. It's just regular neutrino from nuclear burning. And okay, so then the explosions, the collapse start to happen, and that's the transition between, that's time 0. Then from 0 to about 200 milliseconds in this figure, where I shade this in blue. So this is the accretion pre-explosion phase, where we often hear about all the complicated 3D dynamics and hydrodynamics and simulations, etc. So that's what's happening here. And in this particular model, it's a 1D simulation. The explosion happens at about 200 milliseconds, and you see there's a kink at the top of the blue curve. So after that, things at the envelope get exposed. So you expelled, and you're left with a proto-neutron star. So that is the remnant of the collapsed core. And then for the entire blue region, from 200 milliseconds, this isolated proto-neutron star core just cools. So this can be further divided into several stages. The first part of the cooling of the few seconds or so is mental contraction, meaning that mostly what happens is the neutron star core shrink in size. So after a few seconds, the radius comes down to roughly the size of a neutron star, so about 10 kilometers. Then it's just the thermal cooling of a isolated object, and the energy gets carried away by neutrinos. So that's between 1 to 10 seconds. So late cooling, core cooling. And then in this particular model, at about 40, 50 seconds, you see a very sharp drop in luminosity, where it's labeled proto-neutron star is cool enough that end, like fully end of the explosion physics. you could have additional emission source, the accretion disk around this neutron star, then things could fall back onto it at time. So that is neutron star. Okay, so this on physics ground, how to think about the time. They're a little bit differently. So that's like so before explosion, also in the detect explosion, pre-supernova physics, I would say is where people normally consider the main thing. There's a real good physics reason to think that's the case, except for the fact that for supernova at 87A, that's sort of how long the signal lasts. So this 10-second time scale just are imprinted in people's mind. But for the next one, since we can detect so many more neutrinos, the signal will not cut off at 10 seconds. So in our paper, we call everything after 10 seconds late time, but rather follow everything after 200 milliseconds all the way to 100 seconds. Sorry, I see many messages coming from the chat.
Yeah, sorry, Shirley, it said that your audio was breaking up. I was just asking if everybody has the same problem. I think it's on your end.
I see. Okay.
So it's fine. There's probably nothing you can do at this point, but it's okay.
Okay.
So anybody, just let me say, anybody that has their camera on that is not Shirley, maybe turn it off just to conserve bandwidth. But yeah, go on, please. No worries. Shirley? Shirley? Are you there?
Okay.
Okay.
Yes.
Yeah, no, sorry. No, you got lost for a moment. Yes, please go on.
Okay. So let me know if it's a problem again. Hello, can you hear me?
Yeah, I think you're fine.
Okay. Okay, so that's the scale of the time scale of a supernova. Any questions on the slide? No? Okay. So then for the rest of my talk, I will, instead of looking at only late time, I will actually looking at the entire cooling signal. Again, which in this case.
Shirley, I'm sorry to interrupt. Because you got a bit cut off, could you repeat maybe the late time part?
Sure.
Yeah, thank you.
Okay, thanks. So, right. So I was saying that on the experimental side, we often have time scales that's differently. So pre-supernova is its own thing. And for the main signal, really people consider a supernova duration to be, a neutrino burst duration to be about 10 seconds. And as I said, there's no real good physics reason to believe that, except for that perhaps that's how long 87A lasted in a neutrino detector. So we have in mind that it should be about 10 seconds. But for the next one, because we expect much larger luminosity, so we can see the spectrum to much smaller luminosity and also late time, there's no reason to expect the signal would cut off after 10 seconds. So on the experimental side, we define late time as everything after 10 seconds because that's often not considered in experiments. But on the physics ground, really one should be looking at the entire cooling signal altogether. So this is anything that's passed after explosion. So in this particular model, it's from everything from 200 milliseconds all the way to 100 seconds. So that's what I will be talking about next. If there's no other questions, I will continue. Okay, so the first thing, if one wants to study the detection of supernova neutrinos, one need to start with a simulation. And I will not describe any details of the simulation, but just to say that if we want the simulation to go on for a very, very long time, so in this case, all the way to 100 seconds, then we cannot really afford for a very detailed multi-D simulation, because those are so expensive that they don't normally go beyond 1 second. So instead, we want to focus on the cooling physics, which is much simpler, so that one can use a much simpler the simulation with much simpler physics, which means this is 1D, and also in this model, this is the simplest model that we use, so there's not even convection. But the benefit of this model is that it goes all the way to 100 seconds, and we use a 15 solar mass star. And I want to highlight that there's actually way more simulation groups that look at the explosion physics, which I guess is expected, but these simulations don't predict signals beyond 1 second. Whereas in experiment, we really expect things, we can detect things all the way to 60 seconds. So for majority of the signal that's in time in experiments, it's actually very difficult to find simulations that predict such signals. And as the slide suggests, the simulation was done by Luke Robert. Okay, so let's assuming that the simulation is a magic box that spits out the flux. Let's look at what are the basic characteristics of the neutrino flux in the entire cooling stage. So in all following figures, I will show the post-bounce time between 1 to 100 seconds. So I cut off a bit of a signal before 1 second, so between 200 milliseconds to 1 second, because again, this is a 1D model. So the explosion is not treated fully realistically. So we don't quite trust our simulation before 1 second, but after 1 second, it should be pretty robust. And I use a log scale because of the large length. And because I use a log scale on the time axis, I plot luminosity multiplied by t, so that the visual integral should correspond to the contribution. So there's, again, 3 flavors, which mu x meaning that average of each of nu mu, nu mu bar, nu tau bar. So the first thing to see is that all the 3 flavors have very similar luminosity within a factor of maybe 20% at best. And again, this is not surprising because even in early time, except for neutronization burst, we sort of expect that. We know that all the 6 flavors are at first order pretty similar. The next thing we can see is that there's a thin black line that actually trace all 3 flavors quite well all the way to late time. So this is a functional fit where the first part is just a constant. So constant times a super exponential cutoff. Because it's constant on t times L, which means luminosity just falls as 1/t for a very long period of time. Now, depends on your prior knowledge, this might be surprising or not surprising to you, because in the more, I would say, phenomenological field of supernova neutrinos, people have long believed that the flux of luminosity falls off in an exponential form for the first 20 seconds or 30 seconds or so, which turned out that's not at all what we're seeing, but rather it follows 1/t quite precisely for all the way to 30, 40 seconds. And because 1/t seems so simple, we believe that there must be some physics reason behind it, analytical reason, but unfortunately we cannot identify it. And we talked to some experts who also cannot explain this. So if you have any ideas, we'd love to know. But in any case, this is what we see out of simulation. And then, of course, the next thing to see is that there's a super, super sharp drop off at 40 or 50 or so seconds. So that's where in this particular model, the proto-neutron star is turning into a neutron star. So this is what I find cool about studying the late time physics, in that it's, rather than saying this is supernova physics where the complicated hydrodynamics and stuff people have in mind, this is more like studying neutron star physics. So equation of states and etc. Okay, so that's on the luminosity side. What about average temperature or average energy? I might use these 2 terms interchangeably. So here I show the average energy of the 3 flavored neutrinos in the same time range. So we see for 2 things. First is because the physics period is cooling, so things are decreasing in temperature. So as expected, all the curves just go down. But nice thing I want to point out is that not only are the curves going down, but the difference between the three flavors also are shrinking. Now, this has a practical nice benefit in that, as we know, the early time oscillation of the supernova neutrino is extremely complicated. This means that if you want to extract, say, astrophysics, then you have to know how to predict this oscillation to extract astrophysics, which is a very complicated business. But at late time, because the average temperature are all converging, which means that we know the effect of mixing will be small. So if we want to extract, information about a proto-neutron star, then we don't have to worry about mixing because we know the effect will be moderate. So that's a practical benefit because we don't quite know how to deal with mixing. Okay. And lastly is we can look at how much energy is actually contained in the late time. So here I plot two curves, cumulative. The purple one is the total energy fraction as a function of time. And I would say in supernova, there's another quantity that are almost just as important, and that's the lepton number. Because consider before explosion, you have an iron core. After the whole explosion, you have a neutron star. So half of the job is to turn a equal mix of proton and neutron to a neutron-only object. So this means changing lepton number that's carried away by the difference in number flux between neutrino and nu E bar, so which is plotted in the brown curve. So here we see that for the cooling period after 1 second, actually 60% of energy is carried away in this part, and 30% of lepton number change is carried away by everything after 1 second. And specifically, if we look at everything after 10 seconds, so even after 10 seconds, there's still about 20% energy left. And there's still about, I would say, 10% of lepton number change left. Now, those numbers may sound small, but I want to point out that if we want to make a 10% or 1% measurement on these quantities, this means that we must measure the entire flux all the way after past 10 seconds, all the way to probably 40 seconds or 50 seconds. So these are supposed to generally describe what the signals should look like, and that they carry important fraction of the total for the entire supernova explosion. Any questions?
I have a question, if I may. So you were showing a couple of slides ago the constant behavior of the T times luminosity, and then the drop off. Yeah, right. How do you know that this is the right behavior? Like you say that the earlier times you don't fully trust that because it's a 1D simulation. It doesn't really encompass all the physics effects that should be there in a 3D simulation. How do you know then that the late time behavior that you're seeing here is the right one?
Great question. So I guess okay. So I guess first start off, depends on your definition of the right one. I might not know that. So what do I mean by that? So what we can know from the simulation is that all the artifacts, like numerical artifacts from how we trigger the explosion, have disappeared after 1 second. So that you can check just from numerics. So then after 1 second, the luminosity the signal we get is what we get out of the simulation. Now, is this what's gonna happen for a 15 solar mass stars? We're not sure because, like I said, I think in this place, this simulation is actually very, very simple, meaning that there's a lot of physics. There's physics effects that have not been implemented. For example, convection. Convection is something that we do expect happen. It's just at some level. So if that happens, that will change the emission curve here for sure. Not at some level. So not that it completely spoils the behavior, but essentially at wiggles on top. And for example, if it's some other solar mass stars, then that's going to look different. So I guess this is Yeah, but I think it's the same for all the supernova, even in early times, that you can gradually add more pieces to your simulations, but you can only look at what your simulation tells you and hopefully compare to with other groups, so that eventually you converge on what are the basic features that everyone all expects. But but this is definitely not like for sure, oh, for a 15 solar mass star, this will be the curve you get. I don't think we can make that statement yet.
Okay, that's good. Thank you.
Thanks. Any other questions? No? Okay. So then after looking at roughly what we expect, I guess that's the best way to summarize the signal. Let's look at what detectors we have for detecting late time or the entire cooling neutrino signal. So for detection channels, what we're looking for has two things. The first is the cross-section has to be large. And of course, because for neutrino physics, we are always limited. Event statistics is pretty much always an issue. So the larger, the better. Especially for late times, as we'll see later, the luminosity, the flux drops really, really fast. So especially large detectors are needed. But there's another thing, which is the kinematics, meaning that we also want channels where individual events can be identified and that they have some sort of nice relation between what energy deposition you can detect in your detector and what's the energy of the neutrino. So this way you can also at some level reconstruct neutrino spectrum. So I'll talk more about this point later on for individual events, for individual detectors. So consider this, the three best channels to detect the three flavors are lifted on the left on the right, lifted on the left, with the detectors correspondingly on the right. So just the status, so Super K has been running for a very long time and will continue to run for probably a very long time with the successor of Hyper K. Dune is under construction stage that will hopefully get online in, I think, somewhere between 2026 to 2029. And Juno is also under construction stage, but will probably get online in a couple years or a few years, I think. Okay, so now let's look at how each individual channel will look. So the first one is Super K. And again, we put the supernova at 10 kiloparsec. The detection channel is inverse beta decay, which means that you are measuring the energy of the outgoing positron. So first thing is let's look at the event per time being as a function of post-bounce time. So this is very similar to the luminosity curve. And we bin the event with the time bin you can see by the width of the tick marks, and the number per bin is what's plotted. And the number of events after a fixed time is labeled on top. So the first thing we see is that after 1 second, in this model, we would detect about 1,000 events. And after 10 seconds, there are still about 250 events left. And with the last event comes in at about 60 seconds in this model. So where you see down the orange curve where the y-axis across 1. Okay, so the first thing is, well, okay, great. There's actually quite a few events after 10 seconds. So now in comparison to the total number of events, you might think, well, 250 events is not that many, but I like to point out that that's actually about 10 times the number of events that we've detected for 87A. And the last event comes in at about 1 minute. Another thing that's important, which is not shown on the plot, is background. So in Super K, because it's been running for so long, we know what the backgrounds are, we know how to handle them. So it turned out that in the 1 minute time window, we would expect less than 1 event per background for background. So Super K really has a 1 minute background free detection window where we would expect to see the very last event detected. So, which is great news. So another thing that we want to look at is, of course, what are the quality of these events, meaning that how well will the energy be measured? So we did not do an energy reconstruction on the neutrinos for this project, but we look at something simpler just to have a more general idea. So what I plotted is the energy of the positron, but actually in this case, because of the reaction, the energy positron of energy of the neutrino is actually tightly correlated. So measure 1 is the same as the other. You just add or subtract 1.8 MeV. So I bin the time being in the course 4 periods, and I plot the spectrum of the positron, and I take into account detector smearing. So energy resolution has been added. And each curve is normalized to 1. So we see a couple of things. First, going from early to late time, so going from darker to lighter color, we see the average energy keeps getting smaller as expected because things are cooling. And for the last one, so 30 to 100 seconds, the spectrum is quite soft. So, you know, the positron energy has average energy about 7 MeV. That is much lower than what generally you might think of supernova neutrino, which is more like maybe 30 to 50 MeV. So these are very, very soft events. But luckily, the detector threshold is low enough that it's 3.5 MeV, that you are still seeing most of the spectrum, meaning that if we were trying to reconstruct the spectrum, even for the last time window, so 30 to 100 seconds, we can probably still be able to get a decent reconstruction. So, okay, so that's it. So I would say summarize the detection in Super K is that we have about 1 minute detection window. It's background free. The detector energy resolution is small enough. It doesn't make a difference. And detector threshold is low enough. Efficiency is high enough that we should be able to see all the events, have very good quality measurement, and should reconstruct neutrino spectrum, which is great. And of course, I want to highlight that this is inverse beta decay channel where we use Super K as an example, but many other detectors also have this channel. For example, Juno, you know, most detectors have some protons. And so Juno will be able to carry out a roughly comparable measurement. And of course, when Hyper K comes online, the statistical will be even, you know, better, about 8 times larger. So for Nu E bar channel on inverse beta decay, we basically got it done. It's as good as it gets. Okay, and for Nu E, I would say that's really exciting for you know, neutrino nuclear astrophysics because of the upcoming detector Dune. And the reason is this amazing charge current detection window, a detection channel on Nu E. So here is a complicated plot that shows the cross-section as a function of neutrino energy for pretty much all the detection channels we have in all detectors. And let's just focus on 2 channels. So the green curve shows this charge current interaction on argon, and the blue curve shows neutrino electron scattering. And I select this channel because if we didn't have argon, neutrino electron scattering will be the channel that we have to use. And we see first is the nuclear channel has a much larger cross-section, which is great. And another thing is that it has very low thresholds, meaning that for a lot of nuclear channels, let's say if you look at this kind of thick black line, that's kind of prominent. So the cross-section really starts at about 18 MeV. And that's kind of pretty common for a lot of these nuclear channels, that even though the cross-section end up being pretty large, there's almost no cross-section for neutrinos below 20 MeV, which obviously is a problem for late-time detection because late-time neutrinos only have about 10 MeV or 20 MeV. And this argon channel is super nice in that the cross-section is large even for low-energy neutrinos. And additionally, because it's a nuclear channel, which means that the energy of the outgoing electron, energy of the incoming neutrino are pretty tightly correlated, which of course makes reconstruction of neutrino spectrum easy. So we really lucked out in having a really large argon detector, or we will have. So this is the projection in Dune, and similar style to the Super K figure, where we show event per log bin as a function of log time. So first thing to look at is, let's say after 1 second, there's about 610 events. So comparable to Super K, a bit less. And after 10 seconds, there's about 110 events. And again, roughly speaking, comparable to Super K at order of magnitude level. So there's plenty of events. And the last event is a bit closer to Super K, but also quite late at about 40 seconds. So basic characteristics are the same. But there's one big problem. You see this background line. So where in Dune, there will be the worst background will be thermal neutron capture. So what this background is dune is underground, so it sits in the mine. And in surrounding rocks, there's radioactivity. So those radioactivity can produce MeV neutrons. And because the argon detector is now shielded, these neutrons can just come in and capture. And when they capture, they emit back MeV gamma rays, which will be a background. And the background rate is just really, really high, 4 Hertz. Now, it's a constant background, but it scales linearly because I'm plotting essentially T times dn dt, which is why it goes up. But you see that if this background cannot be distinguished from the signal event, then it's going to overwhelm the signal at pretty early time, about 20 seconds. This will be really bad for dune because then it's missing the last bit of the tail, which later on I'll describe what physics can we get with the last bit of tail. So in principle, it has enough events, but there's this really bad neutron capture background. If they can somehow reject this background or shield it, then the prospect in dune is also pretty nice. An additional thing we want to look at is the spectrum. So here, because I assume that you detect the outgoing electron, so that's what's plotted on the x-axis, and similarly, coarsely time bin spectrum plotted. So here, if we look at the last time window, so 30 to 100 seconds, so you see what I mean. So this spectrum is so soft that if you have a detection threshold about 6 MeV, then you're really only seeing the tail of the spectrum. So you're missing the peak and more than the peak. So this means that if you were trying to reconstruct the spectrum between 30 to 100 seconds, it highly depends on your theory prior because you're only measuring the tail. So which means the quality of the reconstruction will not be high. So this is just to say that for dune, because the threshold is higher, you have to make sure that the detector threshold, because the interaction threshold is higher, you have to make sure that detection threshold is low enough, at least below 6 MeV. Now, because liquid argon this is the first time we've carried out large-scale liquid argon experiments, the performance at MeV is extremely uncertain. So what threshold exactly we can reach, these are all unknowns. So it's very important for the experiment to invest in their MeV capability to make sure that they can push the detection threshold down enough to see most of the spectrum. Okay, and another thing is on the theoretical difficulty of this channel, which given the time I will skip, but I'm happy to talk about it later, meaning that basic summary is we don't know the cross-section well. Okay, but I won't talk about that. So last channel I want to look at is μx, which is very exciting in Juno because μx is very difficult to detect. But in Juno, in liquid scintillator, we can have this channel of μx scattering on proton, where this proton can make a little bit of energy deposition in liquid scintillator detector. But as you can imagine, this proton doesn't actually give you much energy, so this is a very difficult detection channel. So here I again show the event, the spectrum, so the event light curve as a function of time. So here, first thing we notice that there's much fewer events, unfortunately. So after 1 second, there's only about 200 events. And there's only about 10 events after 10 seconds. So just because this channel, the proton gives you very little energy in your detector to see, the efficiency is very low. This is just as many events you can see. But still, there's non-negligible events at late times. So 10 events is not nothing. If we can see them. And in Juno, there's another problem of detector background. This is actually come from carbon 14, so very little you can do about that. And the background rate is about 0.7 Hertz, 0.7 Hertz. And if you want to push for lower detection threshold, this background rate will rise up by orders of magnitude. So the background rate is uncertain. 0.7 is about a standard estimate. Okay, and this, but on this channel, not only will see fewer events, we'll also not really measure the neutrino spectrum, or at least very difficult. So here's what I mean. So the energy of the proton comes out only in the really fraction of the true kinetic energy, meaning that detected energy is much smaller than neutrino energy. So here on the x-axis, I plot they actually deposit the energy in your detector. So first you see that these are very small numbers, so only by 0.1 MeV or 0.2 MeV compared to 10 MeV neutrino coming in. And this is just because of how protons show up in liquid scintillator. So all these spectrum peak at essentially zero time, as zero energy. So if you have a detector threshold of 0.2 MeV, then you can only see really the tail of the spectrum, even for the very early time from 1 to 3 seconds. And because you can only see the tail of the spectrum, the reconstruction of neutrino energy will be very difficult. So this is just the kinematics of the interaction channel. So there's basically no way to come back this. Still, if they can push down the detection threshold from 0.2 to 0.1 MeV, they can see a lot more events. So that's very important, but extracting spectrum will be difficult. So this channel is just intrinsically hard. Okay, so that is a survey of all the 3 channels to cover all the 3 main flavors in 3 experiments. Any questions so far?
I have a question.
Go ahead.
Oh, I have a question. When you were talking about the background in Dune, you were saying that those are MEV gamma rays.
Yes.
Do you know in what range of MEV? Is it any or?
Good question. So it's neutron capture gamma rays. So it has a pretty wide distributions. The softest ones are like 0.1 MeV. The hardest one I think is 6.2 or something MeV, somewhere around 6 MeV.
Okay, thanks.
So there's like 100 or so capture lines. So there's one at 4 point something MeV. There's one around 6 MeV. So those are the most problematic ones.
Okay, thanks.
Thanks. Okay, if there's no other questions, I will continue to demonstrate, to explain the one physics case that we demonstrate of what you can do with a very late field events that you cannot get from early time. So that has something to do with observing black hole formation or neutron star formation. So let's look at this green line. So that's our standard nominal model where you have a successfully exploded star at about, again, 0.2 millisecond, 200 millisecond. And then you're left with a proto-neutron star that just cools. And eventually at about 60 seconds or so, this proto-neutron star, it just successfully cooled and turned into a neutron star. So that's our nominal model that we simulated. Of course, at various points, the story can go in a different direction and you get a black hole instead. So the first scenario is what I labeled case 2. It's a failed supernova. So this is perhaps more intuitive, where at early time, at about 200 milliseconds, when a star tries to explode, so for various reasons, for example, there could be too much matter on the star that the shock just doesn't have enough energy to expel what's outside it. So if this happens, then it will just collapse under its own weight and form a black hole. So this is the failed supernova case, in which case there will be no optical supernova whatsoever. So for the accretion phase, when the star is trying to explode, we still get basically very high neutrino luminosity. And then when a star collapses into a black hole, the luminosity will just sharply drop to 0. So if this happens, I think typically we have in mind that this would happen in early time. So, about anywhere, basically within 1 second. But in fact, when this happens depends on the structure of the progenitor star. So in a reasonable range, this can happen really anywhere between a second to about a minute. So that's case 2. But say even if we successfully explode a star at the explosion point and left with a proto-neutron star that cools, it can still turn into a black hole, because when a proto-neutron star cools, it can trigger, depends on the equation state, it can trigger a phase transition and then just collapse because it just cannot support its own weight. If this happens, that's labeled the case 3 case, case 3, a mass field of proto-neutron star, then at anywhere during the cooling phase, so let's say tens of seconds, it can just sharply turns off and turns into a black hole. And so there are various times where this can turn into a black hole, and not just in the early time. So this is actually so for supernova 87A, this is actually a still open question, which I somehow find a little bit surprising. So because for 87A, because of course on the neutrino side, we did not see what happens. So then the way to figure out what actually got formed is to observe the remnant. So there has been a very aggressive 30-year astronomy program trying to observe what is that thing in the middle of supernova remnant 87A. So here is a list of the upper limit on the central remnant. And this is taken from a review article in 2018. So as of that time, there's still no detection of the central object. And last year, there's a paper that got a lot of press release that they basically actually tentatively detected the central object. So actually this paper is sometimes interpreted as that they've detected a neutron star in the middle, which is not what they say. So in the middle, I show the one sentence screenshot from their abstract. So they say that one of the possibility is a compact object is detected in the middle, but even that, they actually did not give definitive words. So here I just show 3 images from the paper where the central object, if we're there, would be the little blue contour in the middle. And just to give you visual to see that it's actually very, very difficult to see. And even the detection of the remnant is not for sure. So let alone telling whether it's a neutron star or a black hole. And the reason is just there's a lot of dust that obscures everything. So for 87A, the word's still out on whether that formed a neutron star or a black hole. So luckily for the next one, we won't have to do that. So given a standard expectation, I think for the next one, we're pretty confident that we can directly observe the formation of a neutron star or a black hole from neutrino signal. So this plot shows, you can read it this way. Look at the right y-axis, where it shows the detection significance of a black hole if it forms at various times. So if the supernova fails, for example, the black hole forms at about 1 second or 2 seconds, then we basically have infinite statistics significance on confirming that it's a black hole. But even if the black hole forms at 40 seconds, which is a very late time, we can still actually get a 3 sigma detection, knowing that it formed black hole. Alternatively, we can know that a neutron star is formed. So for the next one, really just in super K as it is, we should be able to observe all the way to the last event that tells us whether it's a neutron star or a black hole is formed. So instead of having to wait for 30 years and still don't know what it is. Okay, so that brings me back to my conclusion. So the overall message I really want to convey is that I think on the detection side, because of 87A, people have the nominal numbers from that detection, thinking that with the next one, it's more or less just be the same, just with many more events. But in fact, I want to argue that because it's many more events and much better detectors, we're able to actually carry out precision measurements. So it will be qualitatively different. So one test case that we show in this talk is to measure black hole or neutron star formation directly. But there's a lot more physics opportunities at late times that we hope to explore in future papers. So stay tuned. Thanks.
Thank you very much, Shirley. We have time for a few questions, maybe?
I have one. So I was wondering, in the very late time, if you want to distinguish between your scenario 1 and 3, in principle, I mean, you go beyond the 10 seconds and the statistics that you have is very low. So how can you be sure that you do not confuse case 3 with case 1?
Yes, great question. So I guess I didn't explain the details here. So the key really is that, okay, so first you have to make sure there's no background because that would really complicate things. But what this plot shows is that essentially, even for case 1, even though it drops pretty fast, you still get quite a few events when it drops. Whereas for black hole, you don't get the few events that you get from the dropping. And if you don't see, basically say for the neutron star case, you expect 10 events from this transit when it drops. So the probability of 10 events fluctuating down to 0 and in all future time bins is actually incredibly small, or whatever the number is. So so the probability is actually of confusing a neutron of a true neutron star emission that fluctuate down to 0 that mimic a black hole is actually very small. Of course, if you see any events actually detected, then you know it's not a black hole.
Okay, thanks.
Anybody else wants to ask a question? I have one. So are the detectors being planned to be able to detect late time neutrinos? Or is there like a data pileup, or they're not recording events for some reason?
Yes, good question. So I would say that's only a concern for Dune, and yes, that's a concern for Dune. So for basically regular water or oil detectors, because the data amount is not very large, so these like Super K and Juno, they just continuously read out data, and that's perfectly fine. For Dune, it's a problem because the detector is essentially there are just many like an infinite number of wire channels inside a detector. So the data rate, if they continuously read out data, is actually quite large. So when they trigger on Supernova, they do read out the detector for a fixed amount of time for save data to disk and stop. And it's actually a huge debate over the past few years of how long they should save this data. And I think initially it was like something like 10 to 20 seconds. And now people have been pushing for longer. I'm not sure what's the latest word on that, but yes, that's indeed part of our plan to convince them that you should at least save data to, a minute at a very minimum.
Okay.
Thanks.
So yeah, I was wondering if we could miss actually a supernovae if we don't see the optical counterpart.
Good question. I would say no, not likely. So because the thing is, we'll see neutrinos before optical. So whether there's optical follow-up or not has not much to do, will not really impact the neutrino detection. So the neutrino detection, let's say for the main burst, the best detector, we'll see it in several detectors, even with currently like what's available. For sure, for example, Super K should see it. And I think Super K, knowing that right now they are like the largest one and practically the only one that can get thousands of events, they never turned down, which is actually quite impressive. So I think in 20 years, they only turned down for quite some time last year. And luckily they didn't miss anything. So Super K should be able to observe it. And because I think because experiments know supernova could go off, many detectors will keep a point of keeping up the detector, like making sure the detector is active. And of course, there's actually also pretty aggressive program right now trying to detect the pre-supernova neutrinos. So if we see those, of course, we can only see them if they're very close. But if that's the case, then if people detect pre-supernova neutrinos, they will also send out alerts to essentially all experiments that, hey, keep your detectors on. So I would say because people do know that supernova might go off, there's very aggressive efforts in pretty much all detectors to keep detectors on, including all kind of early warning systems. So I would say highly unlikely. We would be incredibly unlucky if that happens.
Okay, thank you very much.
All right, we have time for a final question. I don't see any raised hands. So let's thank Shirley again for a wonderful talk. Thank you, Shirley. As always, very interesting. And thanks everybody for being here. See you in a couple of weeks for the next Astroparticle seminar.
Thank you all.
Thank you.
Thank
Have
you.
a good day, Shirley.
Bye.
Bye-bye.